Hello everyone. In last lecture I was discussing different types of fatigue design methods. So, based on those fatigue design method, today I will solve some problem on different types of fatigue design method. First of all, in today's lecture I will discuss about reverse stresses design for finite and infinite life. So, you know that the types of problem in fatigue designs generally can be grouped into following categories, like a structural component can subjected to completely what it is called reverse stresses, or it can be subjected to fluctuating types of stresses. Now, the component which is subjected to completely reversing types of stresses, here the following design problem for completely reversing stresses are discussed, that is design for infinite life problem and design for finite life problem, or design for you can say safe life problem. Now, design for infinite life problem is generally based on endurance limit property, you can say. That means, when the component is to be designed for infinite life, the endurance limit, or you can say endurance strength, become the criteria of failure, that we are very well familiar. That means, once a body subjected to a allowable stress which is equal to or below the endurance limit, then generally it will not be subjected to failure due to fatigue. That is why for infinite life problem, what it is called, we generally consider endurance limit or endurance strength is the criteria for design. Now, the stresses which induced in such component should be lower than the endurance limit in order to withstand infinite number of cycles, which I have already told you. That means, here whatever the stress should be induced in those types of component which is subjected to some reverse types of loading, that reverse types of stresses should not be exceeding the endurance limit. Then the body will not be subjected to failure due to fatigue. That means, its life will be infinite. Then such component generally designed with the help of you can say following equation, you can say. Here generally sigma A represent allowable stress, which is generally equal to sigma into Fs, means factor of safety, you can say. Here Fs is factor of safety. Okay. Now, so for if the body is subjected to normal types of stress, then normal endurance strength divided by you can say factor of safety, we use this criteria for designing the component. And if it is subjected to some reverse types of torsional stress, then what happens, it is produced generally shear stress, then allowable shear stress tau A represent allowable shear stress, this should be equal to shear stress due to endurance strength. That means, it is actually endurance stress due to shear, this you should keep it in mind. Sigma SE I have written, this is the endurance strength for shear strength, this you should keep it in mind, and Fs means factor of safety. So, instead of writing sigma SE, we can write tau E also, that means endurance strength due to shear, this you should keep it in mind. Now, we will first discuss about what it is called how to design reverse stresses design for what is called finite life problem. After that, we will solve some problem one by one. So, when a component is to be designed for a finite life, there generally we use SN curve. This SN curve, which I have already discussed in detail, SN curve means stress versus number of cycle curve, which is generally used. So, here this curve generally used popularly for steel types of structural material, this you should keep it in mind. So, as the steel is a very widely applicable material, that is why in this lecture I will discuss the structural component which is made up of steel types of material. So, here SN curve can be used. So, it consists of a straight line AB from generally 0.9 ultimate strength sigma ut means ultimate strength at a number of cycle 10 to the power 3 and 2 endurance strength sigma e at 10 to the power 6 cycle on log paper. How it is, everything in details I will discuss. The design procedure for such problem generally I will now discuss here. So, first of all, for designing this problem, what we need to do? We need to draw the SN curve. So, how to draw the SN curve here, that I am just going to discuss. So, here generally 2 point we need to define. Here defining those 2 point, generally we need to draw a straight line AB. What is those 2 point that I am going to discuss now? Generally this horizontal axis, or this is generally you can called as abscissa. Okay. And this vertical line is generally called ordinate, you know this thing. Now, this horizontal axis represent log base 10 number of cycle n, and this vertical axis or ordinate represent log 10 fatigue strength. Okay. Now, here you see, so first point we need to define in this plot as a, let us say, which I have already told you. So, here A represent the coordinates of A is you can say log 10 to the power 3 comma you can say log 0.9 ultimate strength of the material. That means, here abscissa is 10 to the power 3 log 10 to the power and ordinate is log 10 0.9 sigma ultimate stress. This ultimate stress generally you can say, or ultimate strength of a material is its material property. For a particular material, generally this is constant for room temperature, that you can say. So, this you can write as log 10 to the power 3 is 3 comma log 10.9 sigma ut. Okay. This you should keep it. So, A coordinates is 3 comma log 0.9 sigma ultimate. Okay. Now, another point we need to define, which is B point. So, here let us A is, here this is 3 and here this is, from here to here this is your log 10.9 sigma ultimate. Okay. This you should keep it in mind. Now, here B point we need to define, this B point is equal to your log 10 to the power 6, which I have already told at 10 to the power 6 cycle we need to define these things. So, log 10 to the power will be abscissa and log 10 sigma endurance strength should be its your ordinate. So, this will give us, you know, that log 10 to the power 6 is 6 comma log 10 sigma e. This is this 2 point you need to define. So, B point we got, this B point is, this is your 6 in log 10 log paper, because we know that log 10 n is 10 to the power 6 cycle, that is why it is 6, it is 10 to the power 3 cycle, that is why it is 3. This you should keep it in mind. Now, what are the things we need to do? We need to draw a straight line AB. So, this straight line AB you can say is used for design the strength of that the component depending upon some number of cycle. This you should keep it in mind, because here generally the stress level, the allowable stress in this component generally, which is subjected to finite life types of fatigue design, there generally allowable fatigue strength should be within the limit of 10 to the power 6 to 10 to the power 3 cycle. This you should keep it in. This is generally called finite life cycle. So, this just you keep it in mind. So, that is why here whatever the generally number of cycle we will applied in the structural component which is subjected to fatigue, that structural component should have a number of cycle less than 10 to the power 6 cycle, and it is more than you can say 10 to the power 3 cycle, that you can say. Within this level generally we our number of cycles should lie. This you should keep it in mind. Now, for let us consider for a number of cycle n, we need to define the what is fatigue strength. We need to find out what is SF. This we want to find out. So, for that what are the things we need to do, that step I am just telling. So, first of all we need to draw a point on abscissa or horizontal line, you can say here log 10 n we need to first locate. After that generally this through this point, let us this point is I am just defining as point phi. So, you see through this point we need to draw a vertical line which is parallel to ordinate, which generally cut the AB line at a point let us F. So, corresponding to this cutting point we need to draw a horizontal line which is parallel to, you can say which is parallel to abscissa and which is cutting the, you can say ordinate at a point E. So, here you should keep it in mind, here EF is parallel to, you can say abscissa. This you should keep it in mind. Now, I am just drawing another line which is horizontal to abscissa. Let this line is BC line. This you can say. Now, here how we can find out what it is called this fatigue strength. So, this we need to find out, this fatigue strength will be generally log 10, let us consider this is SF. So, based on this number of cycle what should be the SF, that we can easily find out from this diagram. How we can find out this from this diagram, that little bit I am going to discuss. Here you see here triangle ABC and triangle AEF. From the similarity condition what we can write, from the these two triangles similarity condition we can write AE divided by AC is equal to, you can write as EF divided by CV. So, from this criteria you can say we can easily find out what it is called log 10 SF. SF is the fatigue strength. So, how to find out little bit I am just discussing, you know AE is, you can say log 0.9 ultimate strength minus E means log, all have a base 10. So, I am not writing these things again and again, sigma SF divided by log AC means log 0.9 ultimate stress C is your log endurance strength AC, this will be equal to your, here generally EF is log n minus 3 divided by, you can say 6 divided by 6 minus 3, this you should keep it in mind. So, based on this relationship here generally everything is known, and endurance strength known, ultimate strength generally known. For a number of cycle, if n is known, then we can easily find out what is log SF. So, from this log SF generally we can easily find out what is SF. SF will be 10 to the power generally whatever the value will be there, whatever the value will be there. So, SF we can easily find out. So, these are the steps generally we used to follow to find out fatigue strength of the component based on finite life design. So, SF is the fatigue strength of the component. Now, for this design component, if there is provided a factor of safety, if there is provided a factor of safety Fs, that is your factor of safety, then generally here allowable stress sigma A, allowable stress will be this fatigue strength divided by, you can say, factor of safety. This you should keep it in mind. So, based on this generally what happens, we can easily find out what is the dimension of that component, that means we can design the component as per this design criteria. Okay. Now, we will solve one problem, first on infinite life problem, after that second problem I will solve for finite life problem, then it will be very clear to you. Now, for infinite life problems, here I am just solving one example. So, it is also for reverse types of loading. Here till now whatever the fatigue design related things I am discussing, these all are related to reverse types of loading. We have not yet come to fluctuating types of loading. So, fluctuating types of loading I will come later on. So, in subsequent lecture I will discuss about fluctuating life types of design problem also. So, here I am just solving a general problem for infinite life design. So, what is the statement of this problem? Generally I am just reading this statement, then it will be very clear to you. A component machined from a plate made of steel. So, it is a steel material. This steel material is generally here you see 45C8, it is some nomenclature. This material have a ultimate strength which is 630 MPa which is given. So, this is the machine component you can say which I am showing in this figure. It is subjected to completely reverse axial force of 50 kilonewton. It is also given here. This is the axial load along axis. This force is acting, that is why it is called axial load. Now, it is generally subjected to completely reverse types of axial load, whose axial force magnitude is given as 50 kilonewton. So, here I am writing P is equal to 50 kilonewton. Okay. This is the axial force. Now, the expected reliability here is considered 90%. The factor of safety is also considered as 2. The size factor is given as 0.85. Now, determine the plate thickness T for infinite life. So, for these fillet types of component, you see this is a fillet types of component because it is subjected to a step. Okay. The step, after that generally it is subjected to this P value. Due to this step, you know, there is a chance of what it is called fatigue failure in this lower radius or lower width zone. How it is, I will just discuss that things also. So, we need to determine the thickness of this plate for infinite life. Here we consider the notch sensitivity factor is 0.8. So, what are the things here given? So, I will solve this problem. So, first of all reverse load which is given as 50 kilonewton, then here ultimate stress or ultimate strength is given as 630 MPa. Generally ultimate strength is Popper term, because this is the maximum stress or it is a property of the material, that is why maximum strength is Popper terminology is ultimate. So, it is subjected to complete reversal. The expected reliability is 90%. So, as the expected reliability is 90%, that is why here what are the other vector is given. So, Ka is given as, you can say, what is the Ka value is given 0.76, okay. Kb is given as, size factor is given as 0.85, okay. Then here you see factor of safety FOS is given as 2. So, what are the other parameter is given for reliability factor 90%, 90% reliability, we know this Kc is equal to, you can write as 0.897, 0.897. These are the things already I have discussed in previous lecture. So, here notch sensitivity factor Q is given as 0.8, okay. So, as it is a reverse axial load, so here load factor, you know this load factor generally we consider as Ke, load factor is Ke is equal to, you can say 0.85. Here temperature effect is not considered, that is why you can say Kd temperature effect parameter generally is Kd is not considered. So, here it is generally 1, and here we need to find out this Kg value. Kg value generally we need to find out, we know Kg equal to 1 by Kf. This is well known to you, actually I have already discussed. Kg is called stress concentration, based on this stress concentration factor, whatever the value is coming, based on this thing generally Kg is find out, where Kf is known as, you know this is called actual, or you can say fatigue stress concentration factor. I have already discussed all these things in previous lecture. So, first of all what we need to find out? We need to find out what endurance strength of this material. So, based on Marin's equation, we know endurance strength equal to your Ka, Kb, Kc, Kd, Ke, Kg into 0.5 for steel, generally 0.5 into ultimate strength, correct. These are the things is very well known to you. So, here Ka, Kb, Kc, Kd, Ke, everything is given, only what we need to find out? We need to find out Kg value. So, here generally for finding out the Kg value, there is available some standard data for these types of plate generally, and these are all experimental data, you can say. This is generally some published and some standard data. So, here generally based on this you can say fillet ratio, you can say here d by d ratio is given as, you can say what is the d by d ratio. Here capital D, here you see this is your D, capital D is given as 100 and your small d is given as, this is your small d, small d. So, this small d is given as 50. So, d by d is 2. So, here generally based on this d by d ratio, here you see based on this d by d ratio, let us for 2 what should be the, you can say, KT value if the fillet radius, here fillet radius is given. So, generally here another things also you should keep it in mind, this plot which I am showing how to use, that also you can learn from this example, that is why I am showing all these things here. So, here d by d is 2 is given. So, we need to use this curve, you can whatever the this curve is there, we need to use this curve data. So, first of all this is selected based on d by d ratio, because based on different d by d ratio, capital D by small d ratio, there are different curve is given, like this curve is given for d by d ratio of 1.5, this curve is given for you can say d by d ratio, capital D by small d ratio of 1.2. So, how to use this curve, that also I am showing here. So, here another things also for this curve, this stress concentration factor KT, which is theoretical stress concentration factor, this KT is generally plotted for different fillet radius versus a small diameter or a smaller dimensional width of that component. This you should keep it in mind. So, here R by D, which is given as, you can say R is given as 5 millimeter, 5 R means 5 millimeter radius. Okay. So, this 5 R means 5 millimeter radius and D is given as 50. So, this will give us a value of 0.1. So, corresponding to this 0.1, so here this horizontal axis of this curve is represented R by D ratio. So, here corresponding to this 0.1, you see we need to draw a vertical line, you see this is the vertical line, we need to draw a vertical line. This vertical line where it will cut this capital D by small d curve, from there we need to draw a horizontal line. In this horizontal line, generally whatever the value you will get in the ordinate of this curve, that generally of this curve, this ordinate will give us the KT value. So, what is the KT value generally based on this we are getting? So, this value is actually 2.27, from this curve we can easily find out. So, here generally first what are the things we get? Here from based on these two information d by d, capital D by small d ratio and fillet radius by a small d ratio, what we got? So, KT we got 2.27. Now, here there is a relationship between KT and KF. So, there is a relationship between KT and KF. What is the relationship? That I am going to discuss. So, we know this thing that KF is equal to 1 plus, you can say Q into KT minus 1, correct. This is the things I have already discussed. Depending upon the notch sensitivity factor, there is a relationship between KT means theoretical stress concentration factor or you can say elastic stress concentration factor, and KF equal to generally fatigue stress concentration. Always you should keep it in mind, for calculation of this kg generally we need to take KF stress concentration factor, that means fatigue stress concentration factor, not KT. So, KF is required to find out here. What is KF? So, KF we can easily find out, that is actually your 1 plus notch sensitivity factor is given as 0.8, and we have got this KT value is 2.27 from this right side curve, you can say from this right side curve minus 1. So, this will give us a value of KF equal to, you can say directly I am putting, so 2.016, this is the KF value. So, this KF value I have also told you, this KF value generally always less than KT. If there is a notch sensitivity effect if we will consider, then this is always less than KT. If notch sensitivity effect is not considered, then KF equal to KT. This also I have discussed. That means, if Q equal to 1, at that time KT is equal to KF. Now, here as we consider this stress concentration factor in our this fatigue analysis. So, what is the AC we will get, that I am just discussing now. So, here you can say Ka is given as 0.76, Kb is given as 0.85, okay. Kc is given based on 90% reliability 0.897, then Kd is given as 1 because temperature effect is not given consider. So, here Ke is given as it is the axial types of force, Ke equal to 0.85 and Kg equal to your 1 by Kf, Kg equal to you can say 1 divided by Kf. So, 1 divided by Kf, that is actually I found out that is 1 by 2.016 into 0.5 into ultimate strength is given as 630 MPa. So, based on this, what is the endurance strength we got? Based on these things we got the endurance strength, you can say is 76.96 megapascal, or you can say megapascal mean Newton per millimeter square, because 1 megapascal is equal to 1 Newton per millimeter square. This you should keep it in mind. So, you see now what are the things we need to find out? We need to find out the thickness of the plate, this T. So, we need to find out what thickness of the plate.